But when we go to multi-core, things get worse. On a single processor, the interference between tasks is limited to context switch points. At a context switch point, you have to worry about whether you need to save and restore registers, dirty cache, and so forth. With multi-core, it's happening all the time. The whole time that things are running, they're interfering with one another. And they can interfere in obvious ways. The one of them can put something into the cache, and the other one kicks out of the cache. Okay? And yeah, you have a multi-way associative cache, but it only has a certain number of levels of associativity, and you hit that limit, things start getting evicted from the cache. So you have fighting over the same cache lines between things running. How much fighting you have depends on what they're doing. You know, what part of memory they're addressing, how is their data structure, what are the strides they're making through their matrices, if they're working on matrices. Okay, and it's completely application-dependent logic, completely timing-dependent as to how they phase with one another and coincide in time. And then you got other neat stuff that's going on. They have heat protection built in. You don't know it, but you overheated one of your cores, and it got too hot, so they slowed it down for you and didn't tell you anything about it. The Intel speed step technology, they call it. You have your cores, but the cores internally for bus arbitration, for simplicity of logic, one of them has priority over the others in an order. And so if they're competing, this one always wins. And so one of them effectively runs faster than the others, in priority order maybe, a fixed priority order. You have other elements in the system that are not the processors, but actually can become the bottlenecks. You have the memory hierarchy, you have the interconnection between components, between the memories, the caches, and the caches, and the other caches, the cache and the CPU. And then, of course, we have the old I/O devices that are busy out there doing direct memory access. Okay, so simplest kind of a multi-core processor, I stole a picture here of one. Say it had 4 cores, would have a level 1 cache, level 2 cache, which are local, and then some kind of a cache coherency mechanism and a level 3 cache, and more here to control consistency with some shared memory out here, and then maybe more of these plugged into the shared memory out somewhere else. Okay, so if I'm running something on here, its execution speed depends not only on what's in its local cache, but what's happening over here and how it's contending at this level for here. And it's not just contention, it's synchronization. Because every time this guy writes through to memory, all these other caches have to be notified that there's been a change. Unless I accept inconsistency of the cache, which is another story, hard to program then. So even though I don't know it, even though I'm not touching the same location in memory, the fact this guy wrote through to memory is slowing these other guys down because they have to synchronize. They have to synchronize the cache to know that that line has been changed so that later on, when they want to reference it, they know that what they have in cache is not valid. Okay, so we have all these new ways for tasks to interfere. I mentioned some of these snooping delays on the cache. This is logic delays caused by the need to snoop. Conflicts on the data paths, data flow blocking we talked about before, and all these interferences are dynamic. Some of these, just the cache effects I saw in one paper accounted for at least, thank you, 100% variation in execution time. So what we really have is not this beautiful little model here, but something like this. We have the cloud, and the CPUs are connected to the cloud, the memory is connected to the cloud, the other devices are connected to the cloud, and nobody knows what's in the cloud. Okay. If you go to specific machines, you get different answers, and they change. Like this is one of the new AMD multi-cores, and it has 3 buses that run in a circle, basically connecting them together. This is a grid-shaped machine, a really high level of integration, but it's limited to the paths along the grid. Here's an older one that has only 2 cores, but it's got a crossbar switch in it. Okay, so it's clear that this loop here is going to affect the ability to get data from here to here, say, is going to be different from here to here, right? Okay, so different processors on the same chip can have variations in, I mentioned earlier, access priorities up to 400%. More cores means more variability. The trends seem to be getting worse. We've all seen all this before. if you followed high-performance computing and supercomputers and the big computers, the big iron, all of these things have happened before. All these are methods of accelerating computations and parallel computing have all been done before. All the different architectures have been tried before. And people have spent, I know some programmers, when I worked on our supercomputer, they spend a year writing one program, and by the time they're finished, they bought a new computer with a different architecture, okay? And so it's not portable, and it's not clear. It's like a treadmill, trying to develop software for this. I'm afraid we're getting onto the same treadmill. I have to skip a lot of things here. You now have a network on the chip, and now you're into the network modeling, except you can't model it because the granularity is too fine. With a real network, you have big tasks, and then they send data to other big tasks, and you have long execution times and transmission times, small numbers of transmissions. In this network, you're talking millions, billions of transmissions of little packets back and forth just to complete one task. So I don't think you can do network-style analysis. Maybe. But you don't even know what's on the network because the manufacturer won't tell you, or it'll change from one edition of the chip to the next because they redesigned to make it a little bit faster, to make a better benchmark. Okay, so I think we're in trouble. And here's my controversial statement. I think this is the end of hard real-time systems. I have 2 more, 3 more, but that's... and I'm going to try a couple more to get you controversy going before I quit here. I'm going to argue that we should reduce our focus on tasks as semantic units, look more toward event-driven programming models, try to avoid shared memory. I'm going to say tasks are harmful because they implicitly can access all global data, which is the source of all evil in multiprocessor and parallel scheduling. They mix concerns that ought to be separated. They combine the semantics of your program logic with performance concerns of how do you schedule things to meet deadlines in a single package that can't be separated. They limit the concurrency by having you to decide as a programmer how many threads of control you're going to have at the time you design the logic. By hard coding in the parallelism, so we can't tune it. And they limit fine-grained concurrency because they're too heavyweight, and they have only one thread of control per tasks. I'm going to say protected objects are not so good either. They might be a little bit better. But they have locks, which is not good. Locks are a source of delays. If you can do something without locks, that's better, and there's special purpose constructs that you can describe with a protected object, but you can't implement efficiently with a protected object, like a circular buffer, a read, copy, update data structure that don't require locks and are much more efficient on multiprocessors, can be described by protected records, but not efficiently. They create unnecessary contention. Okay, is that enough controversial? I guess. Let's try to stir you up a little bit. Thank you.